Hey guys, Greaves here. Review 22. This one should have been a little bit familiar. I know we went over this, or I gave you this one maybe in an exam during the year. Let's take a look, okay? So what do I have? I have a rod. It's the same situation, but let's just take a look. I have a rod on a pivot point, right? That's allowed to pivot around this particular point right here. And I have a ball of mass M traveling towards it. So I have three scenarios. Hits the ball hits the rod goes up, ball comes back. Second scenario, ball hits the rod, stops, rod goes up. Third scenario, ball hits the rod and sticks, and the whole thing moves counterclockwise. Okay? All right, so one thing that I want to say about this angular momentum business and a ball traveling in a straight line. Okay? I know it sounds strange, but this ball, even though it's traveling in a straight line, it does have angular momentum relative to this point. Even though it's traveling in a straight line. I know it sounds crazy, but look, well, why is that? How can that be? Well, look, let's look at this case where it sticks to the ball. The ball sticks to the rod. And remember, momentum, both linear and angular, must be conserved, right? So when the ball sticks to the rod, doesn't the rod travel in an angularly, like in a circle, right? So it had no momentum before, angular momentum that is, but after the collision, it now has angular momentum. Well, how can that be? Well, the ball has some angular momentum relative to this pivot point, right? And how we find out actually is L is equal to mvr, all right? Anyway, so it's a little strange. Objects traveling in straight lines can have angular momentum relative to a pivot point, okay? So let's continue, okay? So what do I got here? So this one says, all right, so on this graph, draw the angular momentum of the puck, draw the angular momentum of the rod, right? So, and by the way, TC is where they kind of interact, right? So let's take a look. All right, I'm going to say, let's say, I hope this part is pretty straightforward, right? And I have marks, 1, 2, 3, etc., right? So let's just say here, right? Well, let's everyone helps we understand. The rod, what type of angular momentum does the rod have before the collision? But this is in case 1. Well, I hope you said 0. There it is. Right? So there is the rod. All right. What about the ball? Well, the ball definitely has some angular momentum, and let's arbitrarily call it 3. I don't know, I'm just calling it 3, right? So there's to that point right there. I know I have a black pen on this black graph here, but there it is. So here's the puck, right? All right, well, the question is now, what does the rod and the puck's angular momentum look like after the collision? All right, so let's do it up here. Angular momentum before must be equal to angular momentum after. 1 and 2, after, before, whatever you want. So what do I have? L of the puck plus L of the rod has to be equal to L of the puck plus L of the rod, right? So what do I have? 1, 2, 3. So I've given this some arbitrary 3 plus what? 0 is equal to, right? Okay, so now let's see what happens here, right? What do I know happens to the puck afterwards? I know it bounces back this way, right? So it's going to bounce back this way. So I know that I have to have some angular momentum. It's going to be opposite, right? So I'm just going to do, it's in the opposite direction, right? So the ball is going to have, or I should say the puck has to have some, angular momentum negative, okay? So what does that mean the rod has to have? Well, remember, angular momentum must be conserved. So if I'm calling this -1, right, plus what does the rod have to have now? Well, somehow I have to get, right, the momentum before to be equal to the momentum after. And the only way I can do that in this particular case is to give this 4. Okay? So there is now the rod. Right? So, puck, rod, rod, puck, right? So there is the graph for that stuff there, okay? All right, so next question. Rank the magnitudes of the three angular displacements, 1, 2, and 3, right, for which the rod is going to rotate, right? Didn't do very, it didn't really come very well on mine, so let's do this. Theta 1, theta 2, theta 3. And I is the 1 is the greatest, 2 is the medium, right? 3 is the greatest. All right, so let's take a look. How am I going to do that? All right, so once again, momentum must be conserved, right? So let's take a look at this situation right here. I'm just taking a look at the puck, right? So let's just take a look at the puck. So I'm going to make this up. I'm going to say this is going to be, once again, what are our numbers that I picked? This has, let's just give this an L1 of 2. And it's going to bounce back with an L, right? 2. I think I gave this a -1. Okay? Made up those numbers. So what's the change in angular momentum, right, of the puck for this particular case? Change is going to be L2 minus L1. So what is that? -1 minus 2 is equal to what? -3. So this guy had a change of -3. What happens to this guy over here? Well, let's keep this that my L is going to be 2. We're coming to a rest, so L2 is 0. So my change here is L2 minus L1. So what am I going from? What did I say here? 0 to -2 is equal to -2, right? Well, look at what happened right here. When it bounces back, believe it or not, this guy undergoes a bigger change of momentum. Angular momentum, that is, right? Slow. It goes from -3 to what? -2. And what happens here? So let's just say that this guy is going to be my 2 again. This guy here is going to be, I don't know, 1, right? So what's my change? 2 minus 1, right? So 1 minus 2 minus 1, right? So in this particular case, I can reason things out by my change in momentum, angular momentum, that is. And which puck is going to have the biggest change in momentum, right? And that's going to be case 1, case 2, case 3, which is really going to be resulting in, right, the biggest swing of my rod. So this is going to be 1, 2, and 3. And it, you know, really wants a coherent paragraph response, which may also contain figures or equations. And equations are how I did that there. Okay? So that's that guy right there. All right. So let's take a look at 22, number 2. Right? So I now have some wheel rolling down an incline. Okay? And I believe that there is, in fact, friction. Right? So there is friction here. Okay? So what do we want to do? Right? So on the first one, right? On the diagram below, draw and label the forces, not components, that act on the wheel as it goes down the incline. By the way, how do I know there's friction? Without slipping. Okay? So what do I have? All right, so here's my wheel. First of all, I know gravity always acts at the center of mass, and that's straight down. Right? What about normal force? All right, so this is a little finicky, right? It's got to be from the surface, perpendicular to the surface, through, right, the center of mass. So I didn't really draw that very well, but there is Fn. Okay, as it rolls down, we're going to have friction, right, up the incline. Okay, so there are the three forces acting on this wheel as it rolls down the incline. 2, as the wheel rolls down the incline, which force causes a change in the angular velocity as the wheel rolls down the incline? So if I let this go from rest, right, it will in fact start to what? Speed up both linearly, right, and angularly. Why? What's going to make it spin? Well, it's going to be the force of friction. And why is that? Well, because it's perpendicular, right, it's perpendicular, right, to the center of rotation, right, and that's going to, I don't know if I said that very well. It's going to be the force of friction, right, because it's really causing a torque, right? So the force of friction is causing a torque around the center of mass, And that's going to, any, torque is going to cause an angular, change in angular momentum. Okay? So that is A2, I guess you call it, right? All right. For the ramp angle, which is for this ramp angle, the force of friction exerted on the wheel is less than the minimum force of static friction. Instead, the magnitude of the force of static friction exerted on the wheel is 40% the magnitude of the force or component directed opposite the force of friction. So what it's really saying is the force of friction, right, is 40% the weight that's pulling it down the incline, right? So derive an expression for the linear acceleration of the wheel. So let's do that. You know what, I have this piece of paper over here. So let's derive my acceleration. So as always, F net is equal to ma. So what are the forces, right, that are kind of in play, right, in this direction, right? So what do I have? I have mg, I have ff, I have fn. Everyone agrees that it's going to accelerate down this way, right? However, what's the force that's causing this to travel down the incline? Well, right, this is really mg, so it's this component of the weight that's dragging it down the incline, so that's going to be mg sine theta. Okay? Now, so what I really have is, let's say this is positive, right? So I have mg sine theta minus the force of friction is equal to ma. But you're told that the force of friction is 40% of the force that's dragging it down the incline. This happens to be the force of friction that's dragging it down the incline. So mg sine theta minus 0.4 mg sine theta ma. Goes away, goes away, goes away. And I guess this is just going to be, I'm going to do a little subtracting here. So you're going to get 0.6 mg sine. No, I'm sorry. The m already, we canceled the m's already, right? So 0.6 g sine theta, that's my a. Okay, so here's my acceleration. That's the expression for the acceleration down that incline. Okay, all right, next one. In the second experiment, the same ramp, a block of ice with m is released from rest, right? Why is it ice? Negligible friction. Okay. So which object either reaches the ground, if either reaches the bottom of the ramp with the greatest speed? Now, this one wants you to explain it in forces. So which one's gonna hit first? Well, the answer is the block, right? Why is the block? It wants you to know what's happening with forces, right? So here's my block, right? I have mg sine theta, right? Here's my wheel, right? What did I have? mg sine theta, but I also had the force of friction, right? So look, when I add these forces up, right? Forces, this force here, right, is going to be what? Bigger than this force here, right? Because this is ff minus this, right? So what that means is this acceleration is bigger than this acceleration. So if it has bigger acceleration, it's going to be traveling faster at the same at that bottom. Okay? So that's that guy explained in terms of forces. Briefly explain your answer again. Now in terms of energy. All right. Well, what's happening with energy? All right. So in this guy here, what do I have? I just have U is equal to what? K. However, and by the way, and so this is going to be mgh1 half mv squared, right? So we really want to compare that value. But what about here? Here I have U, but now not only do I have U, or I should say all this potential energy is going to be converted to what? Rotational kinetic energy plus translational kinetic energy, right? So when I do 1 half mv squared here, because I have some more energy over here, this value is going to be less, right? So that's that explained with energy. Okay, so that's 22.